Hello, good evening, everybody. As Laura said, I'm Amy Merkel. I'm a research scientist at LASP and a manager in LASP Office of Communications. And welcome to our very first public lecture for our fall 2021 series. It is my great pleasure to introduce James Mason, Dr. James Mason, and there he is. So Dr. James Mason received his PhD from the University of Colorado in the Aerospace Engineering Sciences Department in 2016. As a graduate student, he worked on LASP's successful Minx CubeSat mission, which was named the SmallSat Conference Mission of the Year in 2016. Dr. Mason was a NASA postdoctoral program fellow at Goddard Space Flight Center until 2019 when he returned to LASP as a research scientist, and he now focuses on the solar corona mass ejections and CubeSat designs. Throughout his career, Dr. Mason has worked on over 20 CubeSats and 5 sounding rocket launches in various capacities, from mechanical and electrical design to assembly to environmental testing, software development, and mission operations. He is a leading expert in CubeSats and small sats. He's currently the principal investigator for a CubeSat called Sunset, which stands for the Sun Coronal Ejection Tracker. And they just completed a funded phase A study earlier this year. He's now working with LASP Mission Operations to control the CubeSat mission, which you'll hear more about later this evening. And he is also the deputy project manager on the ESCAPE mission. Both of those missions were designed to gather information on exoplanets. So this evening, Dr. Mason will talk about the rocket launch he supported a few weeks ago in White Sands, New Mexico, along with an overview of LASP's involvement in some of the other CubeSat and SmallSat missions that are launching or have been launched this fall. So thank you so much, Dr. Mason, for joining us this evening, and I'll now turn the presentation over to you.
All right, thanks for the introduction. And just to check, are you able to see my presentation's first slide?
Yes, I can see it.
Cool. All right, thank you. All right, thanks again for that introduction. This is actually a really well-timed lecture. We're right in the middle of all 3 of these launches. So 2 of them have happened in the last month, and the next one's going to be happening this fall. So at least for me, it's like a really exciting time to get to talk about all these things that I'm involved in right in the midst of them. So I hope that my enthusiasm for these things comes through a little bit to you, and you could see that in the slides, but especially in the videos that some of which I've prepared and some of which have been prepared by NASA and others. So there are a lot of videos, and this is Zoom. So if the videos do end up choppy in this live video, there are a bunch of YouTube links at the end that you'll be able to see, watch them without any choppiness. If you're watching this after the fact, there will be links to those things at the bottom in the description below. And if you take a picture of the last slide, you'll be able to get all those YouTube links too if you're here live with us. So let's get started. Okay, so what you're going to see tonight are rockets and satellites. So there's going to be 3 of them. The first one is what's called the rocket Eve. That's a sounding rocket that launched September 9th, so just like 4 weeks ago. The second one is a satellite, a small satellite called Cute. That's a 6U CubeSat, and I'll describe what CubeSats are soon. And that launched on September 27th, so just a week ago. And then the last one is InspireSat-1, which will be the one that's launching later this fall. That's a small satellite also, bigger than Cute, but still fairly small, 27U, and you'll see photos of that later. So on to the first one, the Rocket Extreme Ultraviolet Variability Experiment, Rocket Eve or REVE. So I'm going to give you a couple of background slides, and then we'll get to the videos. I want to make sure that I give you enough background on these things so that when the videos start, you know what you're looking at. But first, a little bit of history about sounding rockets. So the sounding in sounding rocket doesn't make sense immediately when you just first hear it, but it's because these things were first done many decades ago, starting in the 40s, and they made an analogy to in this maritime strategy of sounding the depths of the ocean. So it's like we're sounding the depths of space, just outside the atmosphere. So they call them sounding rockets. So these are small rockets. They're suborbital, which means they don't go into orbit. Instead, they go up and come back down. And the ones that we work on typically go up and come back down in about 15 minutes. They get out of the Earth's atmosphere, and so they spend about 5 minutes of usable time up there. So 5 minutes of like air time because it's ballistic, but it's above the atmosphere, so I call it no air time. And as I said, for the history of sounding rockets, these things go back at least as far as 1945, which was when we had the very first government-funded sounding rocket, and that was done by the Jet Propulsion Lab jointly with the Army. Just three years later, LASP was founded here at CU. It was called Upper Air Lab, but same lab, and it was founded to start taking scientific measurements from space with repurposed V2 rockets. A few years later, this is sort of an aside, but a really interesting aside. In 1956, LASP and Ball Brothers jointly spun off a company called Ball Aerospace, which is like a big deal company today in aerospace. They build all sorts of large satellites and are really involved in a lot of things. So that's sort of some fun history. A couple of years later after that is when NASA was founded in 1958. And ever since then, they've been funding sounding rockets at LASP and lots of other places as well. So ever since then, lots and lots of sounding rockets. And today, this year, LASP and CASA, which is one of LASP's sisters labs at CU, together lead at least four ongoing sounding rocket programs. 2 of those are solar, 2 of them are astronomy. The one I'm talking to you today about, the Rocket Eve, that's one of the solar ones. And over all these decades, what's been really nice about sounding rockets is they've given rise to an entirely new branch of scientific observation of the Earth, of the sun, and of astronomical objects. And that's because the Earth's atmosphere absorbs all gamma rays, all X-rays, and a whole lot of UV. We still get sunburn, so those wavelengths of ultraviolet do reach the surface of the Earth. But as you get to higher energies closer to X-rays, all those get absorbed. So you actually have to go to space to observe, those parts of the ultraviolet. And so that's how sounding rockets really unlock these new regimes. You can observe all of these objects in new light. So this is the Rocket Eve. This photo was taken just a month ago. This is the rocket on the rail, and I'm going to just step through everything you're seeing here before we go to the video so that you have a sense of what it is you're looking at. So from bottom to top, this yellow structure down on the bottom right, that is the launch rail. So that's what holds the rocket up and what guides it during the first fraction of a second before it leaves the rail. And you can see it's also, the photo is taken straight up and down, but it's the rail and the rocket are tilted slightly. That's tilted slightly to the north because this White Sands Missile Range in New Mexico has all of these launchers down at the southern end, and the range extends way up to the north. So the rail gives it its initial little point to the right.
James, can you hear me?
Oh, yep. Yeah.
We can't see your slides advancing.
Oh, you can't?
No, you're still on your very first slide.
Sorry, everybody.
No worries.
Okay, so this is the Rocket Eve. This thing, that yellow thing, is the launch rail that I was just speaking about, that's pointed slightly to the north. And so the rocket itself, on the bottom, we have the Terrier, which is the first stage or the booster of this 2-stage rocket. And the Terriers are basically they're Navy surplus or old Navy rockets that are anti-aircraft missiles that NASA buys and puts on these rockets. The big black section right above it is called a black brant. These are purpose built for NASA sounding rockets by a company in Canada. So that's the second stage rocket. Just above that is the Rocket Eve payload. That's something like 500 pounds or so for this last launch. And just above that is all the control section stuff. So there are radios in there so that we can command the rocket while it's flying and also get telemetry back real time. And on the very top is the nose cone, and inside the nose cone is a parachute so that when this is coming back down, it can land more or less gently and we can get the payload back. So that is the layout of the Rocket Eve rocket, and now I'll show you the video of it. And it's going to be loud, so get ready.
1, 0.
So this is the first stage booster going. It just went out. Waiting for the second stage booster to kick in now. It's like heart-stopping several seconds while you wait, and there it goes, the second stage. You can see the smoke plume behind it. So that burns for, I don't know, some tens of seconds longer, and then falls off, and at that point we're just ballistic for the rest of the flight.
0. That's 1 5.
And this video is watching the Terrier as it comes back down. It's that little white speck that's kind of in the top left of the screen.
That's 2 5. That's 30.
And that actually doesn't land that far away.
That's 3 5.
While the rest of the rocket lands like tens of miles away.
That's
That
40.
second stage booster doesn't. More camera angles and with slow-mo now. Seeing the light and hearing the sound. So that's the exterior footage. We also have 2 GoPros, or off-brand GoPros, that are inside the rocket. One is looking down and one is looking up, and so I'll show you the footage from that now, starting with the one looking down. So here I've slowed it down so you can see the plume, the shadow of the plume in the rocket itself. In and accelerate time just to get through the 16-minute flight, and this video's highlights down to like 2 minutes. So then we despin and then kick off the Black Brant booster, well, second stage rocket, and you can see it there in the aft view tumbling back down. That white area down there, that patch of white, that's the White Sands National Monument. So then about a minute later, we get ourselves pointed at the sun, and this is super accelerated, like 30x in time. In the forward camera, you can see us go up and fall back down like pretty quick. But you can see in the far distance, California and stuff like that. So then we intentionally tumble the rocket back up so that when it's re-entering the atmosphere, it distributes the heat load evenly over the whole thing, and then deploy the parachute. And then accelerate through time again to just come down until you can see the shadow of the rocket and the parachute, which will show up here in the aft view. And then accelerate down to hear a really satisfying clunk as it hits the ground. And falls right on the face of the cameras. We can get in a helicopter to go pick it up. We're showing the professional photographer there that she's on candid camera. Our grad student there is cleaning the lenses. Then we pick up the sections of the rocket and put it in a helicopter to return back to the main base. And you can see another one of Black Hawk helicopters here flying around searching for that nose cone. We like to collect those nose cones. So this is what the sun was doing while we were flying. We were there to observe the sun. We don't take these images. These images are from another spacecraft on orbit. But the images on the right are the spectra that we took during this rocket flight. So that was the main data product. And in a couple slides, I'll tell you why. Why do we care about these spectra? But first, I wanted to show you also that we're a bunch of rocket nerds, but we haven't become jaded and we like to have fun too. And there's always a little bit of downtime during these things, where you're waiting for other members of the team to do their section, and while you're waiting, you kind of can't leave, so you get bored. And I was talking with a couple of the grad students, and they told me that there's a new version of Microsoft Paint that's in 3D. So I made our desktop wallpaper for the command and control computer, a rocket with Eve on it, and a puppy dog face, because that was options in Paint 3D. And then the next day, I think it was, we got to go out to the actual rocket and sign it. And so you could see like the LASP signature here and a bunch of like Tom Woods, the PI, his name there. And then you could barely see it in this photo, but on the top, I drew that puppy dog face. So that actually went into space. To my knowledge, we still haven't found the nose cone, which is sad. I would really like to get that thing back. Sometimes we do get the nose cones back. And if you tour around the LASP building, they're around. Okay, so why did we do this? So the Rocket Eve is its 10th flight since I think 2007 was the first flight. So we launch it periodically. And the big reason for it is it's a calibration rocket for this Solar Dynamics Observatory, SDO, which is a roughly $1 billion NASA mission that has another copy of Eve on board, as well as two other instruments, AIA and HMI. So the movie of the sun I showed you briefly at the end of that movie, of that the rocket launch video, that video was from one of the AIA telescopes. So SDO was launched into geosynchronous orbit in 2010, so it's been up there for 11 years now, measuring the sun's ultraviolet intensity 24/7. Has an almost completely unobstructed view of the sun all the time, which is amazing. But it's also, just like with your eyes, it's not healthy to be staring at the sun for any period of time, let alone 11 years straight. So these instruments do degrade over time. And that's what this image is showing you down here. So these are the extreme ultraviolet channels from the AIA imager. The top row is showing what it looked like at the beginning of the mission in 2010. And the bottom row is showing it 9 years later in 2009 or 2019. So especially on this far right side, with this blue one, you can see it's degraded significantly to the point where it's like almost not visible. And this is actually with some image enhancement to make it pop out more. Especially in this orange one, you can even see the corners are kind of grainy because there's been a lot of image processing to make it visible at all. So it's degrading over time. So we have this version of Eve, which is an extreme ultraviolet spectrograph, sitting in the lab all the time, not degrading because it's not staring at the sun. Every couple of years, we take it to the National Institute of Standards and Technology to calibrate it, and then we launch it. And it gets measurements at the same time as the SDO Eve gets measurements. And comparing those two, then we can correct the on-orbit one on SDO back up to the signal levels that it should see if it hadn't degraded. So then we get a good calibration for Eve. And because it's looking at the same wavelength range as AIA, we can then correct the imager. So these AIA images then also get corrected. So we do that periodically to track how the instruments are degrading over time. Over the past 11 years and for as long as SDO continues. So that's why we launch Eve, Rocket Eve periodically. But it doesn't take up all the space we have available. So we put bonus instruments on there. It's going to be going to space anyway. We have extra space, we have extra mass, so why not use it? So in this photo, what I'm showing you is the instruments of Rocket Eve. In the background here, you can see this silverish, it's an aluminum cylinder. That's the skin of the rocket. And normally that skin continues to extend over all these instruments, but we've removed it and took this photo so you could see what all the instruments are more clearly. On the right, I'm pointing out all the all the main channels from the Eve instrument, and on the left are the bonus ones. So I'm not going to describe all the acronyms because we don't need to go into that level of detail, but we had an SPA OWLS instrument up here at the top. That is now going to be a CubeSat that's launching in a couple of years, that instrument. On the bottom is an SPA XRS, which is a simplified version of what's on the GOES spacecraft, GOES 16 and beyond. And then in the middle is this DAX 55 instrument, which is the same as it's like a carbon copy of basically of what we're going to be flying on the InspireSat-1 mission, which is the last one I'll be talking about tonight. And it's also an upgraded version of the Minx 1 instrument, which is the final video that I'm going to show you tonight as well. So the two SPAs here, those are actually partially built at home in Tom Woods' garage. So he's the PI of the Rocket Eve and built these things at home. They also include like Arduinos, and these red covers on the front here are just to protect it while we're messing around with things on the ground. Those are 3D printed in plastic at home. We did do stuff at LASP as well to build these instruments, like the diodes and filters and things are all delicate and need to be handled carefully, but does include things built at home, which is pretty fun. Okay, so that's the Rocket Eve. Now we'll move on to CUTE. So this is the Colorado Ultraviolet Transit Experiment. And again, I'll go through just a little bit of background, and then I'll show you a video of the launch. So the history of CubeSats, they were started in 1999 is when the standard was defined by Cal Poly and Stanford. And they standardized basically because up to that point, every satellite was like an almost completely unique build, starting over, redesigning the wheel sort of thing. So by standardizing at least some things, you can save money. But also they defined this standard of CubeSat, which is a 10 by 10 by 10 centimeter cube. So by making something so small, it also meant that it's good for education because the cost was way smaller than normal satellites. Then more or less in 2009, the National Science Foundation started funding CubeSats, including one of our own, the CSSWE, which was a LASP mission. More or less then in 2012, NASA started funding really in earnest technology development. So a lot of CubeSats that have flown have been technology development ones. And then a year or so later, NASA slowly started funding science CubeSats as well. And on this top plot, you can see that so this blue is mostly technology CubeSats that have flown. Of the science ones, most of them have been this red slice, so like solar and space physics, so heliophysics type missions. A few Earth ones and very few planetary and astrophysics ones. So planetary is really hard because you have to go to another planetary body, which is difficult even on big missions. Nearly impossible when you're talking about CubeSat scale things, but it has been done at least once to my knowledge, which is the Marco mission that JPL launched. It was two 6U CubeSats that flew independently to Mars along with the InSight lander, and they acted as a radio relay for InSight as it was going through those minutes of terror as the lander's going down. So really cool mission, took its own pictures of Mars as they were going by. Really cool. That might be my favorite CubeSat mission, even though I didn't work on it. And it's an amazing mission. Similarly, astrophysics has some technical challenges that are they're a higher bar than we face with the super bright sun or the super nearby Earth. Namely that astrophysical objects tend to be fainter. And so you usually want really big telescopes with large collecting area to get light. So it's difficult. So there hasn't been a whole lot of astrophysics CubeSats to date, but there have been some, including the CUTE CubeSat, which is the subject here tonight. So this is what it looks like. This photo was taken just in the lobby of the LASP Space Technology Building. You may recognize the front entryway there if you've been to the building. So this is what Cube looks like. I'll show you all the parts now, just like I did for the rocket. So you can't see the instrument, so it's on the bottom side here. It's not visible, but they're there. This on the front is a GPS antenna. This goldish stuff that's all around the outside, that's a radiative coating to help the spacecraft dump heat. You could barely see it, but there's this thin rod sticking out from the side of the spacecraft, which is a UHF antenna. The big diamond shape on the front is an S-band antenna. That's our high data rate downlink. It operates at like 2.4 megahertz, or sorry, gigahertz or so. And so it's basically Wi-Fi frequency. And then there's a solar panel up here on the top, which is one of four. You can't see them very well because they're all folded up and stowed on the left, but there's 3 more panels over on the left side. And then finally, these purplish reflecting surfaces on the top and side, those are sun sensors, so that no matter which side the sun is on the spacecraft, it can always see if it needs to turn the solar panels a certain direction, it can see I need to turn this way to get there. So this was taken from right by the lobby doors of LASP, and it's inside of this case because this was when we were about to take it out to a spot that some of you from Boulder may also recognize, which is on a pull-off on Highway 36 as you're coming from Superior down into Boulder, and there's this little pull-off on the highway that you can see all of Boulder, get a great view of the mountains and everything. And for about a decade now, we've brought all of our CubeSats up here because it's got a nice clear line of sight to LASP, and we can do an end-to-end communications test with all of the plugs out of the spacecraft, at least a little bit of distance, more than we're used to from just in the lab, and we can verify that everything works from end to end. We keep it in this big plexiglass container to make sure that it doesn't get dirty. And then later, this is the delivery of the spacecraft being integrated into the deployer that would then dispense it into space from the rocket. So, rocket video. This is going to loop 3 times, I think. This was last week on September 9th. This is an Atlas V rocket launching from Vandenberg Space Force Base in California. The primary payload on this launch was Landsat 9, which is like a big deal satellite. And similar to the sounding rocket, they've got extra space, they've got extra weight they can take, the rocket's going anyway. So they do these things called ride shares to bring CubeSats along. It was unfortunately kind of cloudy that day, but this video I think is really cool because you can see it just disappear into the clouds, which looks neat. The legacy of an irreplaceable 50-year record. And this is just an animation of the flight, so you can see like the stuff that happens once it got to space and all the separations and all of that stuff, which is pretty cool. So similarly, two-stage rocket. There's Landsat 9 on the top. The CubeSats come out of these little boxes that are sort of on the side after Landsat 9 was kicked off. Then the CubeSats could get deployed. So while that was happening, oh, sorry, I'll get to that in the next slide. First, why did we do this? Why launch Cube? The highest level description of it is that Cube's an astrophysics mission. It's going to be looking at planets transiting in front of other stars. So those are called exoplanets. And just like planets around our sun, they can lose their atmosphere over time. So similar to like the Martian atmosphere has become very tenuous because it's lost atmosphere. That sort of thing can happen on exoplanets as well. And the current state of the art with current observations, even with Hubble, using those observations, you end up with conflicting conclusions about how this atmospheric loss occurs. at what rate the mass loss occurs. So Qt is designed to help resolve those conflicts by having a dedicated mission that's not like Hubble, where the time is extremely oversubscribed. So it needs to do a lot of different science, whereas Qt has to do one thing. So it's going to launch, it's going to survey 12 to 24 short period transiting planets around nearby stars in order to get the atmospheric mass loss rates and atmospheric composition, which you can see in the figure down here. As the planet goes around the star, it leaves this trail of escaping gas. And the transit in this video is showing what transits look like. Of course, we don't see it like this. You look at a dot of light and you see that the light curve dip like you're seeing in the animation down at the bottom. And that dip is dependent on different wavelengths. Here it's highlighting it in the infrared, but you get analogous behavior in the extreme ultraviolet as well, which is what, well, Qt is looking in the ultraviolet. So similar behavior, you get spectral fingerprints that you can analyze. And I apologize to if any of the Qt science team are looking at this, I've collapsed all of your hard work and like amazing science into a single slide and probably butchered some of it. This is not my science area. I'm not a member of the science team here. Instead, I'm a member of the team that's helping operate and commission Qt on orbit. So this is what we were doing during launch. We were all upstairs on the 3rd floor of the LASP space technology building. In the background there is the TV. That's the NASA administrator giving a speech shortly after the launch. We're all happy. Everything was going great that day. When that TV is not showing launches, we actually use it for information about what's going on at our ground station, and that's what's being shown on the right. So I'll step through what's shown here. We've got live feeds from our 2 cameras looking at our antennas, one in the S band, that one that's like Wi-Fi frequency, and just above it is our UHF antenna. We've got a live feed of the whole planet, where all of our small satellites are located at the current time and where they're going to be for the next orbit. We use this computer to command Qt. The one just above, the screen just above it shows critical health, like this, the state of the battery voltage and things like that. So everyone in the room can see that. And on the very top is just a clock and a countdown timer until the next time that we'll be able to see Qt or any of the other CubeSats or small sats that we're operating. So how is Qt doing? Extremely well, actually. It's been an amazing experience for the past week. It's healthy spacecraft. The bus commissioning is complete. Launched on Monday. We were done with bus commissioning on Friday, and we were actually able to have a weekend and just let the automation run the spacecraft over the weekend, which was great. This week we've been doing payload commissioning. Yeah, so it's moving along pretty quickly. And I also have to give here the last bullet a shout out to the amateur radio community, which has been amazing. So the screenshot on the right is the dashboard that amateur radio enthusiasts have put together to receive Qt beacons and show the telemetry. And you can go to this website, see it. They collect, these people are all over the world. They've collected over 9,000 Qt beacons in the last 10 days. Only 5 minutes after Qt was deployed and started beaconing, they got the first beacons, and we were able to decode the telemetry here back at LASP that we got from them minutes later and see that it was healthy, which was so relieving, because we weren't going to see Qt come over Boulder for something like 7 hours or something. So it was nice to see that it was doing well just a couple minutes after it had been deployed and started beaconing. So that was great. All right, on to the last of the missions that I'll talk about, the International Satellite Program in Research and Education Satellite, InspireSat-1. Similarly, I'll go through a little bit of background stuff before showing you a video. Not a whole lot here, because as you saw at the top of the hour, one of the main founders of Inspire is going to be giving the next LASP lecture. So come see that talk for like a way more in-depth description than you're going to get right here. But basically, the history of Inspire, it started in 2015, led by CU and LASP. I think it was selected for a CU Grand Challenge, which is how it got some initial funding, along with several partners, including Taiwan's National Central University, which launched InspireSat-2 already earlier this year. And the bullets over on the right, you can see all the universities and institutions that are involved in this Inspire program. And you can see it's truly international. We've got USA, Canada, France, Oman, India, Singapore, Taiwan, Japan, and Germany. So it's globe spanning. It's really impressive what's been put together for this. And you can see that there are 7 satellites already in development here. One's launched, one will be launching soon, and the rest are in development. So really successful program. Yeah. Okay, now this is what InspireSat 1 looks like. This is when it was doing some thermal vacuum testing. So it's got a bunch of extra cables and things all plugged into it and strapped onto it. But just to point out some of the things that you're seeing here, this is a UHF antenna. It's a tape measure, literally a tape measure from the hardware store. And you'll see video of that from Minx in the next slide. This is one of the solar panels. You can see the other solar panel over here on the right, the big green board. So 2 solar panels in this case. Again, a GPS antenna. In this one, you can see the star tracker. Qt has one of those too. You just couldn't see it in the photo that I showed you. Same one. S-band antenna, similar frequency as Qt. Radiative coatings again to dump heat from the spacecraft, and this sort of conic cylinder thing on the top, that's the interface to connect it to the rocket for deployment. So we built up InspireSat 1, tested it, all of that was done at LASP. We got one of the instruments, which came from National Central University in Taiwan, put it in. We had another instrument from LASP, which was the Minx 1 upgraded thing, that DAX 55 I showed you from the Eve rocket. I put them all in there, and then we were done, and it's going to be launching from India. And so we normally would take a spacecraft with us on a plane, like as carry-on luggage, or drive it. Qt drove theirs out. Minx flew as carry-on luggage to deliver that one. But during COVID, we weren't able to do that to go to India. So we shipped it with a commercial shipping company, FedEx maybe. And you can see it's all packed up here, nice and tight inside this box, Pelican case. It's all super padded. But these little red things that are all over it, those are like tripped accelerometer things. And so you could see the 25G and 50G one tripped. So this was not handled gently, but it was sufficiently, packed and padded well enough that it was fine. We took it out in India and inspected it and tested it, and everything is working normally. But this is basically the reason that we usually hand deliver satellites. So yeah, just a word to the wise. Okay, why? Well, again, the why of InspireSat. So InspireSat 1. So this one actually has 2 instruments that are highly compatible with each other, and they even have a high-level science goal of understanding plasma in both the Earth and Sun's atmospheres. So the first instrument here comes from, this is the Taiwan one. It's going to be looking back at Earth, and it's going to characterize plasma parameters and irregularities in the low and mid latitude ionosphere that impact the accuracy of GPS. So this is from the bigger version of that instrument that's already been flying for years, this image on the top right. And you can see the ion density here over the entire globe. So what happens when there are these like plasma bubbles that form, and there's basically a time variation in the ionosphere, it can impact things like GPS accuracy. If you're trying to triangulate from your phone or from high precision oil rigs or any of those sorts of things that really rely on GPS, and if it passes through one of these time variable features in the ionosphere, that degrades the accuracy of the GPS. So by measuring these kinds of things, we can get a better understanding about the physics that drive these and ultimately improve things like GPS accuracy. And then for the second instrument, that is the looking at the sun. So the purpose of that one is to understand how the corona is heated by observing the basically how much plasma explodes back up into the solar corona, which you can kind of see happening in the movie here. And by getting really specific diagnostics of that, we can understand like one of the most important questions in solar physics, which is how the corona is heated. The solar surface is like 6,000 Kelvin. The corona is 1,000,000, which shouldn't happen because the further away you get from a hot thing, the colder things should be. But that doesn't happen with the corona. And so with the measurements from this instrument, we can sort of distinguish between two different competing theories of how that happens. So that's why InspireSat has these two instruments, and they're compatible. The Earth observing one will look at the Earth during night, and then during the day, we have to point the solar panels at the sun anyway. So we have this instrument that is also looking at the sun. So it was really mutually beneficial there. Okay, I have one last video. It's 5 minutes long. Sorry, we'll run a little bit long for me talking and a little bit shorter for your questions. But this video is really cool, so I have to show it. So this is showing Minx. It's the predecessor for one of those instruments on InspireSat. It's also the inspiration for like how the solar panels are done and the UHF antenna and a whole bunch of the electronics inside. So I don't have a launch video of InspireSat, but I do have this building of one of its predecessors. So that is Minx inside the thermal vacuum chamber, where we can make it look like space. It's in a vacuum in there for testing. So this is deploying of the solar panels. We did this dozens of times and it never failed. It just uses a fishing line wrapped around a resistor, and then we heat the resistor up and it burns through the fishing line. And it works every time. It's pretty amazing. This is the spacecraft sitting on an air-bearing table, trying to point at the sun. It shouldn't be moving. Similarly, in this clip, it shouldn't be moving, but it is. We had to fix it, and later in the video, you'll see what it looks like once we did figure out what was wrong and fix it. This is that tape measure UHF antenna being deployed, similarly held down with a bit of fishing line wrapped around a resistor, and similarly never failed. Even when you put it in vacuum and make it really cold and make the voltage that it's running off of, which is just a battery voltage, really low, it still works. So worst case conditions, it can still burn through that fishing line and deploy. But it is a tape measure, so we wanted to characterize it carefully in this anechoic chamber, see how good the signal is from the antenna at all angles. Similarly, got really high precision measurements that it was exactly 10 centimeters by 30 centimeters by 10. This is that UHF antenna that's up on the roof of LASP. And these are the solar panels. So students, including me when I was a grad student, built all these solar panels. We just used double-sided Kapton tape to adhere them down. And Kapton tape is basically like aerospace duct tape. And then we solder those little electrical tabs at the top and bottom. And here's a time lapse of a whole panel being assembled. It took several hours to finish one panel. And then we would go and put it under a little vacuum bag, suck it down, apply even pressure across all the cells, and then flow power into the cells to make sure that they glow, because that tells us that they're actually working. This is what assembly looked like in computer-aided drawing and what assembly looked like in real life. A lot messier. But we had this really handy-dandy binder that you can see me referring to in the back there. That binder was basically the IKEA instructions that were put together by a high school student, actually, that we had for a summer. Super useful. That was like a lifesaver. We also calibrated the instrument at the National Institute of Standards and Technology. That's where you can see us shoving it into the vacuum chamber there. We also shoved the spacecraft into its deployer to fit check it to make sure that it would really be able to slide in and slide out before we delivered it. Here's the spacecraft properly working, pointing at the sun. Even if you knock it over, it will return itself back to the sun. So we found the problem and we fixed it. And all this shiny stuff on the outside is that radiative coating I was pointing to on the InspireSat and Qt. Everybody loves watching these antenna deployments. And over time, the solar panels can get dusty, so we have to clean them very carefully. And we also had a professor in the aerospace department that was an astronaut. He helped build the space station and fix Hubble, and we had a social at his house, needing him to sign something, and all we had at hand was this box of Cheerios, which he gladly signed. And speaking of signing things, I laser engraved the names of every person that worked on Minx, which is something that we did for all of our CubeSats. Feels really good to have your name on something that goes in space. So that's what all of the names looked like. And then this last clip I'll show you is not launch, but deployment. So Minx was launched to the space station, and then from the space station, it was deployed. It occurred when the astronauts happened to be awake, so they were able to get out their DSLR camera, 4K camera, and take pictures of it as it deployed. So 2 CubeSats were deployed. I know it looks like it's fired straight at the ground, but it did really orbit the Earth for a whole year before it burned up in the atmosphere. And if you CSI enhance this and zoom in, that plate that I laser engraved happened to be the one that was facing the camera. So that was pretty amazing. You basically see our names in space. A lot of strokes of luck for that to have happened. So that felt really good. Okay, so basically, summary, I've got links to all those videos I showed over here on the right, and the 3 main bullets here you can read from the 3 missions. And I will stop there and take questions.
Wow, that was amazing. That was so cool. That last video, well, all of your videos were amazing.
Thanks.
So there's a couple of questions so far, but everybody in the audience, please ask your questions in the Q&A if you have questions. So going back to your rockets, there was a question about how the pointing is done to observe astronomical targets from the sounding rocket platform.
So for the sounding rockets, once they get into space, they can't use any control surfaces that are aerodynamic. They do have fins for on their way up, but that won't work once there's no air to control from. So once they're in space, they do the same thing that most satellites do. They have little gas jets that they can fire really, really precisely to get really good pointing at whatever you need to point at. So for the solar instruments like Rocket Eve, we're just pointing at the sun the whole time. In the sky, we've got a bunch of sensors on the front to tell it exactly where is the sun, so it can fire those jets just right. The astronomers tend to get to have a little bit more fun. They get to actively control where it's pointed during the flight to make sure they're pointing on the right target. They may have multiple targets. Sometimes they'll be looking at comets. That was pretty cool, but they still use that same gas jet pointing control.
I have a follow-on question to that. So where are you guys sitting when the rocket goes off? Because I'm sure you're not as close as the camera.
No, we're not.
That took the video.
Nope. Some of us are pretty close to that too, though. We're basically split into 2 groups. There's a big group in what's called the blockhouse, this big concrete building that's pretty close to the launcher. It's concrete because that makes it safe to be that close. So there's a bunch of us in there, and that's where like all the fire control and all that kind of stuff is happening. And then there's another building that's a little further away, which is where we're sitting, and that's where we are sending commands to the rocket during the flight. So basically everything after the flight, the blockhouse is like, they're not doing much unless things are going really wrong. And all control goes over to us in the uplink room. We're like telling the instruments to do different things during the flight.
So do you have the camera feeding you the video live? Because I'm sure you can't like look out the window and look up.
Oh, we do. Oh, we have like 50 seconds where we all run outside just before launch and we watch it, and then we have like 50 seconds before we have to run back in. And then we have a live feed of the GoPros that I showed the video of. Yeah. We have that, one of them being streamed down during the flight, so we can see that footage during the whole thing, which is really cool.
That's really cool. Okay, so let's see. Now I think they're talking about Cute.
how common is it for the orbital plane of exoplanets to be lined up such that we can see the transits? Given the distance, doesn't alignment have to be really precise?
That is a question I don't have a good answer for, but it's a geometric answer, and I think it's more or less random which direction other solar or stellar systems will have their planets orbiting relative to the way we're looking at them. And so, I mean, ideally, you want the planet transiting right through the center of the star. I don't know how sensitive the measurements are to transits that are occurring like right across the bottom and things like that. If you are interested in getting a better answer to that question, I encourage you to reach out to the CUBE team, the science team, like Kevin France, the PI, or Erica Egan, the lead grad student. And you can, or if you're on Twitter, you could tweet that question to them too at CubeSat.
Yeah, they're very active on Twitter. So
Yeah.
that's a really good way of getting a hold of them to ask that question. Okay, so there's a question about, I think your last video of cleaning the solar panels. So it says, what will people do if one or some of the chips don't light up after a piece of the solar panel gets assembled and tested?
Yeah, so that's actually a really good question. So the way that most solar cells and panels are put together is the cells are attached to each other. They're like welded to each other. So if one of the cells is broken in the string, it's almost impossible to just replace that broken cell because it's really hard to disassemble them then. Not impossible, but very difficult. So instead, what we did on Minx and most of our subsequent CubeSats is separate the cells a little bit and solder the electrical connections just to the board. So if one cell is broken, we can just unsolder those tabs, pull that cell off, and then put a new cell on. So then instead of losing 5 or 7 or 12 cells, which are each a couple hundred, $200 or $300 each, we only lose one. So yeah, that's how we can minimize damage. I think we've only ever lost one cell, but still it'd be a major headache and a financial hit if we couldn't just replace the one cell.
And then the last question is, when's the launch date for InspireSat?
Yeah, it's still right now it's a fuzzy sometime in the fall, that's why that's all I could say. That's the last I heard from just last week, sometime in the fall, which is before 2022 starts.
Right. Last I heard was December, but they're at the mercy of their rideshare. So
yeah. These were originally all 3 scheduled for September, and rockets almost always have some delay. And the Rocket Eve almost had a delay, but we narrowly escaped having a delay. Qt was delayed, but only by a week. And InspireSat's the one that's delayed by a couple months probably. So they did delay, but not too badly.
yeah. So why don't you give everybody an idea of how many CubeSats are still in development at LASP and CU right now, currently?
Oh gosh, it's probably something close to 10. Yeah, LASP is involved in a whole lot of CubeSats, and they're scattered sort of across all of our buildings. There's stuff you can see in SPSC. There's stuff you can see in LSTV, probably the most stuff. And there's stuff also in the CASA ARL building. So if you happen to be a LASP person and you wanted to see those things, sometimes you can reach out and we can show you those things. And they're also similarly diverse topics. There are things for Earth and the sun and astrophysics. So a lot of diverse science. We also have some technology demonstration ones that are going to be flying. So it's a pretty exciting time for CubeSats in Boulder in general, at CU more specifically, and especially at LASP.
Yeah, it's really exciting time for CubeSat technology. So I guess there's a question of why do most of the CU CubeSats seem to be heliophysics domain?
Yeah, so that's not even just CU, like that plot I showed partway through of the history of CubeSats. I think that it surprises me that there's not more Earth ones, and I don't know the reason for that, but the sun is a relatively easy target as objects go to look at, because it's literally the brightest thing you can look at. So you don't need large apertures, large instruments to collect light. Instead, you're more worried about it being so bright that it's degrading your stuff. But CubeSats tend to be short-lived missions anyway, like measured on months or a couple years. So degradation usually isn't a factor. And then there's the funding side of it too. Just there's been a funding line from NASA for heliophysics CubeSats for longer than there has been most of the other divisions. And so that's just resulted in more heliophysics missions having flown and being developed right now. So it's just sort of happenstance in that regard.
And then can you talk a little bit about the pointing accuracy development for CubeSats? We know it's critical for astronomical observations. It's actually really critical now, three-axis pointing for even Earth-based low Earth orbit observations.
Right. Yeah, I don't know the cube pointing requirements offhand, though again, if you tweeted them, they would probably tell you. So we were just talking about this last week because it's going to be performing at the level that they hope. That the pointing accuracy for CubeSats is like on the order of 10 arcsecond pointing accuracy. And they're pretty stable over time too. We've flown multiple missions like the Minx one that was like, the pointing capabilities were like an order of magnitude better than we needed for that mission. They're not an order of magnitude better than what Qt needs, but the current CubeSat capabilities are good enough for Qt's requirements. Otherwise, they wouldn't have been able to fly this mission because they wouldn't have been able to achieve the science.
Okay, so final question, because we're running out of time. I think it's a good one. What do you think the next frontier is in CubeSat technology?
Communications, I think. So even though we've got S-band, that gives us like 1 or 2 megabits per second. That's still not a lot because it's easy to generate data and it is much harder to downlink it, especially if you only have one ground station, you only get about 10 minutes per pass total, and a lot of that can't be used. So per day, you only get something like 20 minutes of downlink time. So you really want that to be the fastest downlink you can possibly do. And this frontier is being actively explored in a variety of ways. X-band has been commonly used on big satellites. We have some transmitters that can do X-band on CubeSats now, which is much faster. Laser comm is a new fancy frontier that's being done that can get you like, I think I've seen like gigabit thrown around, which is like the fastest internet you can get at home. So that would be like unconstrained downlink capability, basically. Of course, each of those technologies, basically the faster the downlink rate, the more precision you need, the more accuracy you need in your pointing capabilities, because the more of the energy is more focused. So you have to be able to point really, really well. And so as the pointing technology has been improving over time, the possibilities for what kinds of downlink technologies you can use has also been ramping up. So I see that as a major frontier, and that should be not decades out, it should be years out. I think that we'll be able to get some really quick downlinks on CubeSats.
All right, excellent answer. All right, James, thank you so much for joining us this evening. Everybody, thank you so much for attending. And if you have extra questions for James, please contact the Office of Communications and we will forward those on to him.